Okay, so we're going to continue on. So we've been talking about percent composition by mass, which is really lead us into empirical formulas and molecular formulas in terms of how to actually calculate them from experimental information. So I think we're at this example. So why don't you take a moment or two and work this example. We want the percent composition of hydrogen, phosphorus, and oxygen in phosphoric acid, which is H3PO4. I'm going to give you some numbers that might be helpful. Hydrogen 1.008, phosphorus 3007, 3097, and we got their oxygen 16. All right, so we're looking for the percent composition of each of these elements in this formula. So come up with what you got. Okay, let's take a look. So just like we talked about last time, in order to calculate the percent composition of each of the elements that are there, you got to start with the molar mass of the entire compound. Again, that comes from the periodic table. So that's going to be 3 times 1.008 for the hydrogen, plus 3097 for the phosphorus, plus 4 times 16 for the oxygen. That gives us a molar mass of the entire thing of 97.99 grams per mole. At this point, what we want to do is basically just take the mass of each of the elements there and divide it by the total. So the percent of hydrogen in this case would be 3 times 1.008 grams per mole divided by 97.99 times 100%. And that will get us looks like we'll go with 3.086% hydrogen. We'll do the same thing here for phosphorus. In this case, there's just one phosphorus, so that's 3097 up on top, divided by the molar mass of the entire thing. Again, times 100%. And that would get us 3097 divided by 97.99 times 100. 3161% by mass phosphorus. At this point, since oxygen is the last one, you could subtract by 100 and obviously add the other two together, and that would get you your missing percentage. Or you could just do the calculation. 4 times 16 for our 4 oxygens divided by 97.99 times 100%. Gets us 65.31% oxygen in this case. Any questions on that there? And again, when you add up your percentages, they obviously should add up to 100%, which they obviously do. A little bit more, a little bit less, depending on rounding, but you should be definitely in the 100% mark there. Any questions on how to calculate percent composition by mass? So percent composition by mass is sort of an important sort of category, because when we go to calculate the empirical formula from experimental information, like we're going to talk about here right now, a lot of times you are given the composition of all the elements by its percent composition by mass. So there are several steps to calculate the empirical formula, which again is the simplest whole number ratio formula what's present when you have experimental information. So earlier we saw if you are given the molecular formula, you could very simply calculate the empirical formula by reducing it down to a simplest whole number ratio. But when you're given more experimental information, there are a few steps that you have to follow to calculate the empirical formula. So let's talk about those steps to actually calculate the empirical formula here. So to calculate the empirical formula, the first thing you want to do is convert your percent composition into grams. So if you are given the percent composition of each element You want to convert them into grams. And as we just talked about, the percent composition should add up to 100%. So a very easy way to convert your percentages into grams is to assume that you have 100 grams of everything. So a lot of times we will assume that we have 100 grams. And what that really does is basically just turn your percentages into grams. The numbers stay the same. You don't have to do any calculation other than basically turn your percentages into a gram. The next thing that you want to do is convert all your grams into moles. And as we've been talking about, it is the molar mass from the periodic table that we use to do that. So we're going to use the molar mass from the periodic table as a conversion factor to convert grams into moles. Now, once you do this, you will now have the moles of all the elements that are there. And what you then want to do is divide all the moles by the smallest number of moles. So for example, let's just say, for example, we had 4 moles of A after we converted it to moles, and we had 2 moles of B. And if these were the numbers that we got once we converted them into moles, what we would do is divide everybody here by 2 moles. And what that would give us for A is 2, and what that would give us for B would be 1. And if you do this and you actually get whole numbers like we just did there when we divide by the smallest number of moles, that would then be your empirical formula. So that would be your empirical formula if all are whole numbers. Or if they are not whole numbers, they're like really close to a whole number, like 2.999, you know, that's pretty much close enough to 3, or 3.02, that's pretty much close enough to 3. So in terms of rounding, you won't always get nice, perfect whole numbers. But if they are super close or just above the whole number, you could round. But they really do need to be really close to the whole number in order to round. Now, obviously, not all cases this will work out perfectly for you. So let's just say, for example, instead of 4 moles of A, we ended up with, when we calculated it, 3 moles of A. Moles of A, and we still had our 2 moles of B. Now, in this case, when we divide everybody by 2 moles, which is the smallest, and it's always the smallest you want to divide by, gives us 1 for B, but gives us 1.5 for A. And this would give us an empirical formula of A 1.5 and B 2. By the way, up here, this would give us an empirical formula of A2B, which would be our empirical formula. Now, we cannot have a 1.5. They do need to be whole numbers. So we do need to clear the decimal. This is considered too far to round. So 0.5 is too far to round up or down. You do have to find a way to clear it. And you could do that by just simple math. 1.5 times 1 is 1.5. 1.5 times 2 is, I believe, 3, and that is a whole number. So what you would do is you would actually multiply this entire thing by 2. So taking that guy and multiplying it by 2 would give us A3B4, and that would be our proper empirical formula, which is all whole numbers. So sometimes what happens when you go to divide by the smallest is you do not get a nice whole number, or you're too far away to round. And in that case, you need to find a common number to multiply the empirical formula by to get everybody to a whole number. As you can see here, we multiplied everybody by that common number, not just a guy that wasn't a whole number. Typical endings where it's considered kind of too far to round, if you end up with like a 0.33, like a 0.5, maybe like a 0.25, a 0.75, these are sort of considered too far to round. So really, in rounding with empirical formulas, especially book type problems, not an actual experiment, but technically book type problems, it's got to be like pretty much on that whole number for you to be able to round, or very, very close to it. Again, if it's kind of above, like, 0.9 or less than 0.9-ish, or above 0.01 or 2 or 3, then, you're kind of getting into the area where you do need to find that number. Any questions on those steps? So these are the steps that you would follow to calculate the empirical formula based on information given to you. So let us look at one with real numbers here and sort of see how it goes. So we'll take a look at the example here together, which is here somewhere, maybe. There it is. We want to determine the empirical formula of vitamin C. It was found to be 40.92% carbon. Let's kind of write them up here so I get right a little bit higher. So 40.92% carbon by mass, 4.58% hydrogen, and 54.5% oxygen by mass. All right. So the first thing that we want to do is basically convert these percent compositions into grams. We also want to take a moment and just add up the percentages. Once again, they should add up to 100, which they do. If they did not add up to 100, you are missing something. So again, in this case, they do add up to 100. So what we could do is assume that we have 100 grams. And basically what that means is we have 40.92 grams of carbon. We have 4.58 grams of hydrogen and 54.5 grams of oxygen. So by assuming 100 grams, basically keeps the numbers the same, makes the math a little bit easier. The next thing that we want to do is convert all these guys into moles. So that's going to require us to go to the periodic table. And if we look on the periodic table, we see that carbon is 12.01 grams per mole. We see hydrogen from the periodic table is 1.008 grams per mole. And oxygen from the periodic table is 16 grams per mole. So using the molar mass from the periodic table, we're going to convert all these guys into moles. So that's going to give us 40.92 divided by 1201. Going to get us 3.4072 moles of carbon. 4.58 divided by 1.008. Going to give us 4.544 moles of hydrogen. And 54.5 divided by 16, going to give us 3.4063 moles of oxygen. Feel like I shorted a number there on the second one. We'll do the same numbers. 4.5437. 437. All right, any questions up to there? So it's really the same calculation we've been talking about, periodic table, grams to moles. At this point, we have the moles of each of the elements that are involved. We're going to divide everybody by the smallest number of moles, and in this case, it's pretty close, but it looks like oxygen here is the smallest number of moles. So what that means is we're going to take the 3.4072 moles of carbon and divide it by 3.4063 moles. We're going to take the 4.5437 moles of hydrogen and divide it by the same smallest number of moles. And we're going to take the 3.4063 moles of oxygen and divide it by the same number there. That is going to give us 1, obviously, for oxygen. This pretty much gives us 1 there for the carbon. And when we do our hydrogen, we end up with here 1.33. So once again, we chose the smallest number of moles, which is what you always want to choose, and we divided all the other moles by the same number. Any questions on that there? Now, this technically will give us our empirical formula, and if we look at it, it would be, at this case, C1, H 1.33, and O. Is that an okay empirical formula? It is not, because once again, they are not all whole numbers, and 1.33 is too far to round. So what we're going to do then is figure out a factor to multiply 1.33 by to get to a whole number. So if we multiply it by 1, we obviously get 1.33. We take 1.33 and times it by 2, that is 2.66. If I take 1.33 and times it by 3, that is 3.99, which is pretty close to 4. So in this particular case, we can actually multiply everybody not by 4, but by the factor of 3. So we want to multiply everybody in that formula by 3. And if we do that, we are going to get C3H4O3, and that is all whole numbers, and that would be our empirical formula in this case. Any questions on that? So once again, the steps are what you see here. Get it into grams, grams to moles, divide by the smallest. Again, if you hit whole numbers at that point, you're done. Put a box around it. If you do not, then you need to figure out a factor to multiply everybody by. Any questions on any of those steps there? Yeah. If two of them don't equal a whole number, what usually will happen in that case is you could find a common number that will fix them both. So usually because they're really all based off kind of the smallest ratio of each of them, you'll be able to usually fix multiples if they're not by the same sort of common number. Yeah. Other questions? All right, let's try one here yourself. Now that I did that one, let's do this one. Chemical analysis of a 1.078 gram sample contained 0.540 grams of sulfur and 0.538 grams of oxygen. What is the empirical formula? Sulfur is 3207 on the periodic table. Oxygen is 16. All right. So follow those steps, calculate the empirical formula here. Grams of sulfur, and we have the grams of oxygen. So we have 0.540 grams of sulfur. We have 0.538 grams of oxygen. By the way, if you add those numbers together, that is what this number represents, and you don't need that number in this calculation. It's just telling you that you're not missing anything, right? So once again, if you added those numbers up and it didn't equal that 1.078 number, then you are missing some type of element mass or something like that, which you could get by subtracting from it. So in this case, we really are just going to take our grams of each of the elements which were given to us, and we would then convert them into moles. So using the periodic table, we would take our 0.540 grams of sulfur, a little 3207 grams per mole, and we'll take our 0.538 grams of oxygen, 16 grams per mole. Going to get us 0.50 divided by 3207, looks like 0.01684. And for the other one there, 0.538 divided by 16, 0.03363. And in this particular case, it is the moles of sulfur, which is the smallest number. So we're going to divide everybody by the moles of sulfur. So obviously for sulfur, if we take 0.01684 and divide it by 0.01684, that should equal 1. And for the oxygen, we take 0.03363 moles of oxygen divided by 0.01684. That gives us 2 in this case, I believe. And that means we did hit whole numbers. So our empirical formula here would be SO2. Any questions on that one there? All right, let's try another one then if there's no questions on that. Yep. Good. All right, try this one here. What is the empirical formula? We got 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen. Once again, carbon 12.01, hydrogen 1.008, and oxygen 16. Okay, let's take a look at this. So once again, we are given everybody in percentages here. So we just quickly look at it. We do have about 100% there given, which means that we are good to just convert these guys into grams. So that would give us 49.3 grams of carbon. That would also give us 43.8 grams of oxygen and 6.9 grams of hydrogen. Once again, next thing we're going to do is use the molar amounts from the periodic table and convert each of these into moles. So we'll do that. So that's going to be, again, 12.01 grams per mole of carbon, 16 grams per mole of oxygen, and 1.008 grams per mole of hydrogen. So converting those guys into moles gets us 49.3 divided by 12.01, 4.1049 moles of carbon, 43.8 divided by 16, 2.7375 moles of oxygen, and 6.9 divided by 1.008. 6.8452 moles of hydrogen. Any questions up to there? At this point, we're now going to divide by the smallest. So it does look like in this particular case, that is going to be our oxygen. So we're going to divide everybody there by oxygen's molar mass and get rid of some of this stuff out of my way, maybe. Oh, you get it. So we're here. I kept it, huh? All right. So we're going to divide by 2.7375, divide by 2.7375, and divide by 2.7375. So in the case of the top one, should give us about, let's see here, going to give us 1.5. This guy here is obviously going to give us 1, and 6.8452 divided by 2.7375 going to give us 2.5. So in this case, we would have C 1.5, H 2.5, and O, which was sort of a question earlier. We do have a couple here that are not whole numbers, and again, are too far to round. So we could probably figure out just by looking at it that maybe if we multiply by 2, in this case would give us 3. And if we multiply this by 2, it would give us 5. So again, you could use the same sort of common number to fix both of them, which is in this case, you want to multiply this guy by 2. And that would give us C3H5O2. Once again, you do need to multiply everything by the 2 in order to get there. So as was the earlier question, again, that common number should take care of everybody if you have multiples that are not, again, whole numbers. Question on how to calculate the empirical formula here. Last little thing we're going to talk about here next few minutes is how to calculate the molecular formula. So when we calculate the molecular formula from experimental information, there's really three things that we need to sort of have to calculate it. And really the three things to calculate the molecular formula is you actually need the empirical formulas. So you do need the empirical formula, and either it will be given to you in the problem or you pretty much got to calculate it like we've been doing. So probably in most cases, you'll need to first calculate the empirical formula and then calculate the molecular formula from it. Once you have the empirical formula, either you calculated or it was given to you, you need the molar mass of the empirical formula. And once you have the molar mass of the empirical formula, what is usually given to you in the problem is number one here, which is the approximate molar mass of the compound. So somewhere in the problem, they'll usually say the molar mass of this compound is this number, or it's approximately this number. Or they may even give you a range, like the molar mass runs from like 90 to 100, somewhere in that ballpark. So they'll usually give you that information. And what you do is you basically take the molar mass from the problem that they give you, and you divide it by the empirical formula's molar mass. And what that will give you is a number. And out of all the places, that number that you get is a number that you can round if you need to. And it's usually a whole number, but if it's not, that's okay to round on that number. And that number you're going to multiply the empirical formula by. So for example, if your empirical formula is X2O1 and you did this and you ended up with a number that was 4, you would then multiply this whole thing by 4 and gives you X8O4, and that would be your molecular formula. So this sort of number that you get is really the multiple that you multiply the empirical formula by to actually get the molecular formula. So let's take a look at one here and sort of see how we would do it. The empirical formula of acetic acid is CH2O. What is the molecular formula if the molar mass is approximately 60? So in this particular case, they gave us the empirical formula without us having to calculate it. And once again, if you did need to calculate it, you obviously would follow the same steps that we've been doing. So what we need is actually the molar mass of the empirical formula. And to get that, that would be 1 carbon at 1201 plus 2 hydrogens at 1.008 grams per mole and an oxygen at 16 grams per mole. And the molar mass here of our empirical formula would then be 3003. So we now have really the three things that we need to calculate the molecular formula. We were given the empirical formula. We just calculated the molar mass of the empirical formula. And what's usually given to you in the problem is the molar mass of the compound. So to do this, what we would have to do at this point is to take the molar mass that was given to us as the molar mass of the compound, the approximate molar mass. We would then divide it by our 3003. So we take 60 divided by 3003, going to give us basically 1.998, which is pretty close to 2 in this case. Now that 2 is what we're going to multiply the empirical formula by to get us our molecular formula. And that means our molecular formula here would be C2H4O2, multiplying that across. Not very often, but sometimes people will write it like this, like CH2O with a 2. But most of the time, probably the better to just multiply that 2 across and write the molecular formula. So those again are the three things that you need: empirical formula, molar mass of the empirical formula, and the approximate molar mass of the compound, which is again typically given to you in that particular compound. Any questions on that? All right, we're going to lay it up there for now. Talk